welcome to Science Hour. I am going to talk about the impact of ocean mesoscale eddies on the atmospheric mean state. It's basically a summary of deliverable D71. You'd be forgiven if you haven't read the draft. It's come out as quite long, of course, as these reports always do. But I'm going to try to kind of give the main, the important summary overview in this talk. And I just want to particularly credit Chris and Matthias, who, besides myself, wrote most of that deliverable, but also the rest of WP7 for making various contributions to this or providing data where necessary. Okay. Yeah, okay, so obligatory funding slide, and also obligatory advertisement for the next Science Hour, which is coming on November 17th, where there are going to be 3 talks with this topics shown here. So there's going to be something about convective systems, something about climate variability and climate change, and something about the Southern Ocean and sea ice. So come along then if you want to learn about any of these things. But for today, it's just going to be a one-man show with just me. Although possibly Matthias and Chris will show up and answer any questions. Okay, so I mean, I think the audience here don't really need a lot of motivation here, but I'll just point out a few things to kind of think about what we might have expected or hoped for with these simulations before having done them. So what might we gain from the mesoscale? One obvious thing relevant in Europe is the Gulf Stream. Maybe we'll get a more realistic Gulf Stream and thereby reduce North Atlantic SST biases. And possibly we even not just change the biases, but we really gain some enhanced variability from the eddies. The figure is showing, of course, somehow the typical behavior of models. So it's the multi-model mean SSTs in winter on the left. So you've got a Gulf Stream which separates from a continent early and then just moves zonally across the Atlantic. While in observations, of course, we know the Gulf Stream separates earlier and then in particular does this nice northwest turn. Oh, can I get a laser pointer? We do that. Okay, I don't know. Maybe you can see my mouse. Hopefully you can see my mouse moving around. Oh, maybe it's this actually. I got it. Yeah. Okay. So you've got the northwest corner coming in the real world, but it doesn't happen in models, in low resolution models, and you get these big SST biases. That's what you're seeing on the right as a result of that, including this big blue blob in the North Atlantic, which can be a really massive bias in many models. So just to elaborate briefly on this thing about maybe we'll get some extra variability. So there was this nice, there was a few papers suggesting this. One, which I always liked, was this paper by Yang et al. In 2024, showing that essentially the relationship between SST gradients and heat fluxes seems to be much higher in real kind of high resolution observational products. That's the star up in the top right corner, compared to what you get in models or reanalysis data. So it suggests that maybe resolving these eddies in models could lead to substantially greater heat flux variability and therefore precipitation variability over places like the Gulf Stream. And then obviously maybe you get some impacts on the atmosphere. However, the counterpoint is that other forecast-based studies are a bit more equivocal on this. So there are 2 in particular, one by Chris Roberts et al. In 2022, and then more recently by Reynolds et al. In 2025, and they both in different ways look at the impact of having resolved eddies on the forecast, and generally find little to no impact on atmospheric forecast skill. So I'm not going to basically tell you what this plot is showing. The point is it's comparing forecast with and without eddies in various ways. And the key point is just that you can't really distinguish them clearly from each other, which is suggesting that the eddies in this forecast didn't really do so much for T850, so temperature at 850 skill. Okay, so the spoiler alert for what's about to come, and this is in a sense the main executive summary perhaps of this deliverable, is that, well, we've seen before already by the work in WP6 that there is a big step change in the ocean, but as far as the mean state is concerned, at least, there's only a modest impact on the atmosphere. And I'm saying that now because I'm going to show you a bunch of plots. I mean, I've tried to limit the amount of figures I'm showing you, but there's going to be quite a few anyway, unfortunately. So I'm just telling you this so you have this in the back of your mind for how to interpret what I'm showing you. Okay. So I'm going to be basically looking at the ERIE frontier simulations, which you know the details of, and comparing them against, besides comparing against observational products, I'm also comparing to past models at lower resolution, non-eddying simulations, so CMIP5, CMIP6, and high-res MIP. And that's kind of important. I think it's important to obviously have a kind of baseline model context to understand to what extent the changes we see in ERIE, or changes in biases, say, are consistent with what we have seen before, or if they are kind of big dramatic changes in some way. So let's start with a kind of flagship thing, a flagship metric, which is just global average surface temperatures. Here's annually averaged time series from 1950 to 2015. For the ERIE models, here's the colored lines, and various colored lines. ERA 5 is in red, and then the gray lines in the background are various CMIP6 models. So I've plotted this as absolute values rather than anomalies, so you can see something about the spread in the mean state as well. And well, a few features pop out. First of all, quite obviously, the IFS NEMO simulation came out very cold, which was, of course, disappointing to the people involved. But and of course, it was even colder at some point. But then, thanks to model work, it was made less cold. But it nevertheless is still has the dubious honor of being the coldest CMIP6 generation model, let's say. But you know, it's not like wildly outside actually what CMIP6 models do anyway. So and pleasingly, it does show some global warming, which I'll say more about in a second. The other ERIE models do pretty well generally, or just look fine. Let's say fine or very well. So the scatter plots on the right are trying to give an indication of how the change in both the 2-meter temperature mean, so that's the top, and the 2-meter temperature trend, how those things depend on resolution. And just to give you an idea of what kind of how changes in the ERIE model might reflect changes in atmospheric or oceanic model resolution. So as you might expect, for the mean 2-meter temperature, there's not really much dependence on the resolution across models. So I should point out the black dots now in these scatter plots are just a variety of simulations from CMIP6, CMIP5, and high-res MIP. So there's about 130 dots in most of these. And then the ERIE models are, of course, the colored ones. And then you've got the histogram of the y-axis on the right. So generally, there's no dependence on resolution or kind of model generation on the 2-meter temperature mean. This is, of course, because there's a lot of tuning going on to get the global energy balance roughly correct, and therefore getting the 2-meter temperature roughly correct. And it's the same with the area models. For the trend, there's also only a weak relationship with resolution. But the main point here is just that actually the trend of area models is completely normal, including for IFS Nemo. So IFS Nemo is hidden under the icon blue diamond here. So despite the fact that IFS Nemo is very cold as a mean state, it has a completely normal global warming trend. And everyone else, yeah, just has kind of normal global warming. So nothing terrible or like amazing or crazy happened in these resolutions with respect to this key metric, so that's good. Let's look a little bit at the actual spatial pattern of biases though. So again, now focusing just on 2-meter temperature for winter now, DJF. So top left panel, we've got the Era 5. On the top right, it's the CMIP6 median bias. So the median across all the CMIP6 simulations at each grid point. And then we've got the biases for the 4 ERIE models underneath. So you can see this cold bias of IFS Nemo here, and a kind of interesting feature is you can see it's not, the bias isn't really massive everywhere. I mean, it's big in the Arctic, but then that's typical for CMIP6. So it's not anything unusual particularly. What's unusual is just that it has a really persistent bias. So it's just negative, slightly negative bias almost everywhere. More striking is ICON, where you will see certain biases, like over North America, for example, here, that are very unusual compared to what you get in CMIP6, and we'll see more of that. Later. As for IFS Fisom and HAGEM, they basically look good, fine or good. They perform generally quite well with respect to 2-meter temperature. So, I mean, again, this is one of these things where if you have a favorite model or you ran this model, you can, of course, stare at these plots to your heart's content later and kind of try to think about all the small scale differences. But yeah, I'm only going to be looking at the large sweep. So precipitation then. Again, it's like now it's I-merge as our observations and the CMIP6 median bias. Top right, and again, the ERIE model biases underneath. So what do I want to highlight? Let's highlight ICON again straight away. ICON has big biases in the tropics. And my understanding is that it's because the convection parameterization is not on in these simulations. And it seems that the model can't simulate realistic precipitation or convection just by itself at this resolution. So you get big biases in convection, and these are going to have knock-on effects for the circulation elsewhere, as again I'll show you in a little bit. But the other 3 models, again, you can stare at them in detail later if you like, but if you glance between these 3 models and the CMIP6 median bias, you'll probably believe that they're mostly normal looking. So again, like not dramatically better, but not dramatically worse either, just kind of normal looking. You can get a slightly better maybe sense of some of these things by looking at these zonally averaged plots. So it's winter at the top and summer at the bottom. And now the black, the shading is like the minimum and maximum of the CMIP6 range. And you can see that now you can see in particular like how ICON's precipitation is well outside what CMIP6 does. Interestingly and quite amusingly, HAGEM in green here also is way outside what CMIP6 does in summer at least. And it turns out that Hajim does some strange things in winter. I dug into this, and it turns out there are a couple of grid points near the coast of Burma where the mean precipitation in DJF exceeds 100 millimeters per day. So yeah, I don't know why. But I just want to emphasize, so it's big enough for buyers that you can see it in these kind of plots. But if you look at the spatial maps, you won't, it's sort of you can't really see it. It's just a particularly red dot somewhere, right, which won't really be visible. But when you take these averages, you start seeing it. But I want to emphasize that Hajim, of course, otherwise, besides these, few like strange grid points, performs very well. Okay, so I've been saying a few times already that the biases are mostly normal. How might, you might wonder how you can quantitatively say that. And one thing we ended up doing, making plots like this. So what I've done is I've taken the grid point biases at every grid point and pooled them to make histograms. So the gray histograms now are when you pool the grid point biases for all of these CMIP6 models. And then the colored histograms are for the various ERIE models. So essentially, if your colored histogram is within the gray, it means that you're doing better than CMIP6, on a per grid point basis. While if you're outside, you're doing worse, right? And so you can kind of see that it varies a bit from between season and between precipitation and 2 meter temperature. And you can see some of these features that we've already highlighted. So, for example, Hajim's strange precipitation in summer, and Icon's biases just generally, and also the cold, some of the cold biases of Nemo. Well, actually, sorry, no, take that back. You can see some of the biases from Hajim and Icon, but interestingly, you can't see Nemo popping out. So even in 2 meter temperature, it has, okay, there's, maybe occasionally it's sticking out, but by and large, IFS Nemo does sort of okay, which comes back to this point that the bias in IFS Nemo is generally small, like at each grid point. It's just a consistent negative bias. Okay, if it's getting a bit like...
Chris, can I ask you a question about that plot?
Yeah, you can.
Are you okay to be interrupted? So, so at each grid point, so you're not regridding the higher resolution models first, because the higher resolution models can have higher extremes. And so that would come out of this plot if you're looking at the value at each grid point.
I am regridding.
Pop out because they've got bigger extremes, or not?
Oh, I am regridding. Sorry, I should have said this. Everything's been regridded
all right.
to 1 degree before doing all this stuff. So hopefully,
thanks.
Hopefully that doesn't kind of come into the picture. Yeah. Okay. So anyway, yeah. So maybe I don't know how easy it is to, like, if you've not looked at this kind of plot before, I don't know how easy it is to like just quickly look at it and get an intuition about what's going on. But the takeaway is that in general the biases are typical in most cases for CMIP6 models. They're not like horribly outside or horribly inside on average, the CMIP6 distribution. Okay, let's look at a few specific examples, though. One thing which is, of course, of interest is with precipitation is the double ITCZ bias. And unfortunately, that doesn't seem to be fixed at 10 kilometer, at least not in these simulations. So how am I measuring that? Well, so I'm kind of highlighting in the top plot here the double ITCZ bias in summer. It's this kind of, the double ITCZ bias is primarily or mostly a feature of tropical Pacific, and it's this excess precipitation here. And what you can do is you can take the average precipitation in that region across the modern period, 1980 to 2015, and plot that for a bunch of models and stratify it according to model resolution, as I've done here. And what you can just see is that the value of this double ITCZ metric is basically the same. I mean, it's consistent just with past biases. No clear indication that there's an improvement with resolution in general. And that's consistent with some previous studies as well, but generally the resolution doesn't seem to have much of an impact. So this is a bit depressing, but even at 10 kilometer, there's no kind of clear sign that we're about to have a step change down. But there we are. Let's move on now to, let's just move on to circulation biases. So again, I don't want to I'm not going to dwell in any detail on the features of this plot. You should just read the draft, the submitted draft report if you want to stare at these more. The main thing I'll just highlight again is that the biases in Icon's convection really can be seen in the circulation. So these are zonal winds, by the way, zonal winds in winter by latitude. So you can see the tropical convection leading to big changes in the overturning circulation, and as a result of that, big biases in the jet streams. But the other three models are basically just look pretty normal. So the comparison, by the way, here with the CMIP6 median bias isn't entirely fair, because the individual bias, the individual biases are all mostly correspond to the jet moving back, the jet's moving around a bit. So when you take any kind of median or average, you kind of tend to smooth it away a bit. But if you compare these biases of IFS FISOM, IFS NEMA, or HAGEM to individual CMIP6 models, they look just very similar in magnitude as well. Okay, energy budgets. So here I'm showing top of atmosphere, shortwave radiation at the top, and longwave radiation. At the bottom, again stratified by resolution, and you can see this is a nice story that all the models are performing particularly well and are sort of continuing a trend that we've seen since CMIP5 and probably from earlier as well, that models have just become much better at doing the radiative budget over many years or decades of model development. Although it has to be emphasized that probably past studies suggest that this is mostly just due to better parameterization, so better radiation parameterizations, for example, and better aerosol forcing, and it's probably mostly unrelated to resolution, including the eddies. But it's nice to see that the ERIE models continue this trend. Okay, so that's a kind of really quick overview of some of the coupled model changes. Now, the other part of this deliverable is trying to quantify in some way or another what the eddies are contributing, or how the eddies are contributing to any of these changes we've seen. And we're doing that using these sensitivity experiments that were run out of ETH Zürich by Chris and Matthias. And the idea is to split the contribution of eddies on the atmosphere into two parts: a kind of direct effect. Direct just meaning that, well, if you have an eddy somewhere, then it has an immediate local impact on the atmosphere. And so if you have lots of eddies, then they have lots of local impacts, and they all add up to a mean state impact. But the indirect effect is rather that having a model which is able to simulate eddies is going to change the mean state, because it's going to change It might change things like the Gulf Stream separation, or more broadly, it might change ocean heat transport. So you change the SST mean state, and that obviously then will have an impact on the atmosphere. So the direct effect is a kind of time varying effect, and the indirect effect is the more time constant effect. And we studied the direct effect using those sensitivity experiments. So the control experiments here are just an ensemble of simulations with prescribed SSTs. So you've got the correct time constant mean and the time varying eddies. And then you have a smooth anomaly, a smooth anon counterpart, where you smooth away the time varying eddies. So now you've got the correct time constant mean, but you don't have the time varying eddies. So you're kind of removing the indirect effect and looking at trying to isolate this direct effect by comparing these two. Okay. So Matthias has made lots of great plots looking at eddy composites, which you might have seen before. So basically, what you do is you apply tracking algorithm to track hundreds of thousands of eddies in the Southern Ocean, and sorry, hundreds of thousands, tens of thousands, maybe I should rather say. And then you create composite plots. So this is looking at, I'm just highlighting here the composites using the high resolution IFS. So SSTs, 2 meter, 10 meter winds, heat fluxes, and precipitation. And these are eddy-centered composites, which is what these kind of the white circles are indicating. You're centering the composites always on the eddy that has been tracked. It's a bit maybe not so easy to see like what's going on here. So it's kind of convenient to try to look at anomalies in some sense. There are various ways you could try to convert those into anomalies, but one nice way, or one way which Matthias anyway favors, is to look at anticyclonic minus cyclonic. So you do the composites for the anticyclonic and then the cyclonic, and then you subtract them with the idea that they sort of opposite to each other. And this really highlights the or is a way you can think about it as showing the anomalous impact of the eddies on the atmosphere. So now in the top row, we've got estimate from observations, and then we've got the low resolution IFS. So that's 28 kilometer resolution, and then the high resolution 9 kilometer. And you can see that actually the IFS looks fairly similar to observations at both resolutions, although perhaps not in the 10 meter wind speed response. So there's a kind of some interesting differences maybe in the 10 meter winds, which could be looked at later. But otherwise, they look about right. And I didn't include this, but if you do this, so we did the sanity check, but if you do this eddy compositing for the simulation with the smoothed anomalies, then you basically get 0 anomalies in the composites here. So, so we have checked that the smooth anomaly experiments are doing what you expect. They are removing exactly these imprints from the atmospheric variability. Okay, so what impact does that actually have on the atmosphere? So again, so it's this kind of summary plot showing various things. Winter is on the left column and summer is on the right column. So it's latent heat flux, 2 meter temperature, precipitation, and cloud cover. And this is using the low resolution 28 kilometer IFS because the impact of the eddies seem to be the same. And we have more ensemble members at this resolution, 10 members, so you can do some more robust significance testing. I don't want to talk you, again, I'm not going to talk you through all the features or explain to you all the stippling and shading. The key point here is that if you just look at the figures, you'll notice that the impacts are generally small, right? There aren't many places where you have lots of color in the plots. And where you do have robust impacts, it's generally the places you expect them to be. So eddy-rich regions like the Gulf Stream, Croatia, and Southern Ocean. So for example, you can look at wind in precipitation, you can look at the Gulf Stream region. You get increase in precipitation here along the Gulf Stream in both winter and in summer. And you get changes in the Southern Ocean, changes in cloud cover in particular, come out as quite robust and consistent across seasons. But away from these eddy-rich regions, the impact is generally small. However, there is a suggestion that these impacts, these changes to the mean precipitation in these boundary currents those changes are having an impact on the atmospheric circulation. So now we're showing more kind of large-scale circulation differences. So Z500 at the top, zonal winds at 300, and meridional winds at 300 at the bottom. And maybe, I mean, I always find it easier to look at what the zonal winds are doing. So you can kind of see some interesting suggestions of shifts in the jet. So for example, the North Atlantic jet maybe is moving northwards a little in summer and has a more kind of trimodal change in winter. There's interesting suggestion of changes in the Pacific, again, which can be interpreted as shifts in the jet. Yeah. To look at these a bit more, or at least focus in on the North Atlantic. Okay, sorry, let me start again. So we see these circulation shifts in the Pacific and North Atlantic, and probably it's related to this enhanced precipitation around the Croatia and Gulf Stream. So there's a lot of literature on this kind of stuff, and actually, if you attended my science hour last year, then I spoke about this at more length, and in particular on the link between the Gulf Stream precipitation and the North Atlantic jet stream. So Matthias looked at this in those results that I shared then in the context of ERIE models. So we're looking basically at changes to Gulf Stream precipitation here in these violin plots. Yeah, I always find this find it hard to look at this plot for some reason. So I'll just summarize. I'll just tell you what it's telling you, what it's trying to communicate, which is that there's a slight increase in the mean precipitation in the Gulf Stream and an increase in the 99th percentile of daily precipitation in the Gulf Stream region. So it's not just that the mean goes up, but also the intensity of the extreme precipitation in the Gulf Stream goes up in both summer and winter. And that is consistent, including through my own work, it's consistent with downstream changes in the jet, including maybe northward shifts in the jet, which we saw on the previous slide. And to give you some ballpark ideas for those of you for whom these numbers might mean something, the typical kind of latent heating increase we see in these regions, like the Croatia and Gulf Stream, are somewhere between 4 and 10 watts per meter squared. In the seasonal, these are seasonal means I'm talking about. And in precipitation, the increase in the mean is a little less than half a millimeter per day. Okay. So I showed you before, I'm going to skip back. I showed you before this interesting change in the total cloud cover in the Southern Ocean on the bottommost row. So this kind of, we were not expecting this, but it popped out as a really robust, seemingly really robust feature across in these sensitivity experiments. So also in the HADGEM, so HADGEM, there are HADGEM counterparts to these sensitivity experiments at low and high resolution, and again you get this very consistent response from of the eddies. Sorry, response to the eddies in the Southern Ocean of decreased cloud cover. So we looked at it in the coupled models, sorry, I didn't need to go back. I've got it right here. Yeah, so we've got this decrease in cloud cover, and we looked at it in the coupled models. So that's what the scatter plot is showing. So again, I've basically just put a box around a broad Southern Ocean domain and computed the total cloud cover in that box for all these CMIP 5, CMIP 6, and high-risk MIP models using the black dots, and in our 4 ERIE simulations, the colored symbols. And interestingly, if anything, in the coupled models, the direction of change is the other way around. So there's been a weak trend towards having more clouds in the Southern Ocean as resolution has gone up and models have been developed. And the ERIE models actually neatly continue very clearly this same picture. But of course, the point is that this is the opposite direction of change to what you expect from these sensitivity experiments, which was a decrease in the cloud cover. So it suggests that, okay, this might be robust. Probably is robust, a robust direct impact of eddies in the Southern Ocean. But what happens when you couple to the atmosphere, when you bring in the coupling and just allow the whole coupled system to adjust, and so you also get the response of the atmosphere and increased atmospheric resolution, and those changes completely dominate and give you a signal which goes in the opposite direction. Okay, where am I? 40 minutes in, and I'm at my conclusion slide. So there are more plots. I mean, there are many more things I could have shown from D71, but yeah, I don't want to overwhelm you too much, so I'm just going to stop there with my conclusions, which is, first of all, there doesn't seem to be a clear step change in the atmospheric mean state at 10 kilometer resolution. Biases are mostly comparable to CMIP 6, and the improvements we see are kind of as expected. So, for example, the Gulf, it's good to see that we get more Gulf Stream precipitation extremes, but it's basically the expected change. So, if you extrapolate what you expect from past model improvements, the ERIE models are just basically the expected change rather than any kind of step change. And similarly elsewhere. Secondly, the direct effect of eddies can be detected. So these sensitivity experiments do seem to be able to isolate robust impacts, but they are modest, especially compared to things like intra-annual variability or intermodal variability. So they are hard to see a lot of the time in the full coupled simulations. And a consequence of that is that the indirect effect of eddies is likely to be by far the bigger effect. So the fact that the eddy-rich models are able to simulate hopefully better ocean circulations and better ocean heat transport is going to change the SST biases, and that's going to change the atmospheric mean state. And that is the dominant effect of the eddies, it seems, on the atmospheric mean state. Of course, it remains to be seen what is going to happen with atmospheric variability. That's going to be the topic of the second deliverable in this work package. But yeah, as far as the mean state is concerned, this seems to be the conclusion.